Hello, I'm Maruk Said, your microbiology guide. Let's explore in-depth micro techniques and uncover groundbreaking insight together on this educational journey into the fascinating realms of microbes.
Batch fermentation and batch culture explained. Table of contents. Batch culture definition. Principle. Process. Applications. Limitations. Batch culture definition. In batch fermentation, all the medium components are added to the reactor at the beginning of cultivation, except for the atmospheric gases, acid or base for pH control, and anti-foaming agents. Nutrient concentrations continuously change over time, making the system unsteady. Microbial metabolites can be produced during either the primary or secondary stages of the microbial cultivation period. Fermentation is stopped when either all the nutrients are consumed or the target product concentration is reached. Batch culture offers a reduced risk of contamination or cell mutation due to the short growth period. It requires lower capital investment compared to continuous processes for the same bioreactor volume. It provides greater flexibility to accommodate different products or biological systems. It achieves higher raw material conversion efficiency due to the controlled growth period. If you have watched till here, don't forget to subscribe to Family of Science Lovers. Press the bell icon button so you are always updated. Batch culture principle. A batch fermentation system operates as a closed system. At time T equals 0, the sterilized nutrient solution in the fermenter is inoculated with microorganisms, and incubation is carried out at an appropriate temperature and gaseous environment for a defined duration. During the entire fermentation process, no additional substances are introduced except oxygen for aerobic microorganisms, antifoam agents, or acid base for pH control. The medium composition, biomass concentration, and metabolite concentration typically change continuously due to cellular metabolism. Following inoculation and cultivation under suitable physiological conditions, the growth process typically follows 4 distinct phases: lag phase, log phase, stationary phase, death phase, batch culture. Batch culture process. A batch culture process starts with sterilization, followed by inoculation of the sterile culture medium with microorganisms, typically comprising 2 to 5% of the total volume. The concentrations of nutrients, vitamins, microbial cells, and temperature can vary throughout the reaction cycle. Proper mixing ensures that these components remain at acceptable levels and temperatures. The process is conducted under anaerobic or aerobic conditions by bubbling oxygen in or out as needed, while acid or alkaline solutions are added to regulate pH. Anti-foaming agents are introduced when foam formation is detected by a foam sensor. Microorganisms are allowed to grow for extended periods, ranging from days to weeks or even months. During the lag phase, little to no growth occurs initially as the microorganisms establish a physiochemical equilibrium with the environment. Once adaptation is complete, the culture enters the exponential or log phase, characterized by rapid growth. Primary metabolites are produced during the exponential phase, with their synthesis declining once growth ceases. For example, Saccharomyces cerevisiae produces ethanol as a primary metabolite. Upon entering the stationary phase, cells begin producing secondary metabolites, such as antibiotics. For example, Penicillium crassigenum synthesizes penicillin as a secondary metabolite. The batch fermentation process is terminated when one or more of the following occurs. Microbial growth halts due to nutrient depletion or accumulation of toxic byproducts. A predetermined fermentation duration has been reached. The target concentration of the desired product is achieved. Batch culture applications. Batch culture is advantageous for the production of biomass, such as baker's yeast, and for the synthesis of primary metabolites like lactic acid, citric acid, acetic acid, and ethanol. In the food industry, batch cultivation is used to produce organic acids, e.g., lactic, citric, and acetic acids, which serve as preservatives or acidifiers. It is also applied in the manufacture of alcoholic beverages such as wine, beer, and distilled spirits, including brandy, whiskey, and rum. Batch culture supports the production of sweeteners like aspartate and amino acids, such as monosodium glutamate, which are commonly used as flavoring agents. If you have watched till here, don't forget to subscribe to Family of Science Lovers. Press the bell icon button so you are always updated. Batch culture limitations. In batch culture, microbes face constantly changing environmental conditions due to nutrient depletion and accumulation of waste products. Once the endpoint is reached, the process must be restarted, which involves significant downtime. In large-scale bioreactors, emptying, cleaning, and refilling the system can be time-consuming. Low productivity is often a result of high downtime between consecutive batches for cleaning, sterilization, and preparation. The accumulation of toxic metabolites during fermentation can inhibit both microbial growth and product synthesis. Thank you so much for watching. Don't forget to subscribe to my channel, press the bell icon button. Thank you!